Okay, so today we are going to start one another family of deep learning, and that is recurrent neural network. So till now we have seen CNN and fully connected networks, and we like m- most of the time we were dealing with image based problem. Okay. So how to solve image classification, image object detection. So these all are related to the image or uh, or videos. Okay. So whenever you have image based or video based problem, you can go with CNN. And at the end, if you're doing the classification, you can use fully connected. Now let's see, suppose we have another type of problem. Suppose you have NLP problem, natural language processing. If you have text-based problem, now how to deal with that particular problem? So if you have text-based problem and if you go with fully connected, it will not work properly because in the text there is sequential information. There is that sequential relationship. So if you just directly apply fully connected, it will be not able to capture the that sequential based information, that relationship. Even you cannot apply CNN directly because CNN is mainly for the 2D structure. Like if you have 2D structure or 2D matrix, you can apply it. And if you know that there is some spatial relationship there in that 2D structure, then that can be applied. Like you can apply the CNN. But if you have text, like text is totally separate, different type of data. So here, in a direct manner, you cannot apply CNN. Okay. So then what should we do? So if you have text-based problem, you want to solve that problem. Suppose you are going to solve sentiment analysis. You're going to do sentiment classification. Now there, you have given the paragraph or sentences, and your goal is to the goal of the model is to decide what is the sentiment inside that paragraph, whether this is positive sentiment or negative sentiment or it's neutral. So these all the things you want to get from the model. But for that, your model should understand this. Your model should understand the paragraph. Now the thing is, this is totally different type of data. Now, how should I give this to the deep learning or neural network? So fully connected can be used, but again, you know that fully connected, just focus on the input only. So it does not consider the the relationship between the sequential data or sequential samples. Okay, so you can apply fully connected, but fully connected will also not work properly. Then we should be having something which can help us to capture the sequential information, to capture the that relationship between all those sequential data. Okay, or all those words when we are doing the sentiment classification. You could be having a lot of different type of problems like summarization, then maybe asking something from the text. So a lot of different type of problems where you need to capture sequential information. You need to find the relationship between all those words, and that could help you for getting the final output. So let us dive into this recurrent neural network, and this is mainly built for solving the problems which are related to the text or which is having the sequential type of data. So we have seen this type of network before, and this is your vanilla neural network. So even your CNN or fully connected was working in this way. Those all those architectures were working in this way. So what was the thing? You were giving the input, and this is the neural network, and then you were getting the output. This simple CNN or fully connected that we have seen before. Okay. Now you could be having this type of problem where this will not work. So this is called one-to-one mapping. Just given the input, get the output. And in between, you'll be having the function. And this is the function is what? Your neural network, either fully connected or CNN or combination of fully connected and CNN, or you could be having some other type of network also. Okay. Now, suppose you have this type of problem, like one to many. So you have one input, but you want to get multiple outputs. Okay. Let us take one example. So example could be image captioning. So you have given the image. You have just single image. And your goal is to describe this image. So for the describe, for getting the description, you should be having a lot of words, and each word will be treated as a separate output. So that means you have to, like, model has to predict a sequence of words. Okay. So this means it should be having multiple outputs. One output will give you one word. Okay. So if you have this type of problem, again, simple vanilla network will not work. Okay. So even in this case, your RNN will help you, because RNN is having that power that it can capture the sequential information, or it can give you the output as a sequence of samples or sequence of words. So this is another problem where you need RNN. Let's see other problem. Suppose you have video classification. Now, in the case of video classification, like this is called many to one problem. So you have given video, and video, you know that it's like sequence of images. So you have sequence of images, and then model has to give the label for that video. So suppose you are giving some video and like giving one video, one clip of video, and then you are asking model to do the classification of it, like whether this is what is happening inside the image. Suppose person is walking or jumping, like those are the classes. Walking, jumping, these are the classes. Just showing the video, because here you do not have image. In the case of image, you are giving just one image and getting the output, getting the classification. But now here the thing is, like, we have multiple images in sequence, and the model has to give the class for all those for all those images, just looking all those images. Okay, because it's not like only see one image and give the output. No, your model has to see all those images, and then it should take the decision, like what is the class. So this is, again, you have here, it has to capture the sequential information, because here we are having a sequence of images, and it should capture the information from all those images and then give the label. Okay. So this problem is called many to one, because we have many images, many input, and the output is one. Okay. So it has to get one. It has to give one output. Then we could be having many to many problem. So, like, we have multiple inputs and multiple outputs. So the problem could be, like, just take one example. This, suppose you have machine translation. So you have to translate one language to another language. Okay. So give the sentence or paragraph of one language. Suppose you are translating uh, from Hindi to, or maybe English to, some maybe Tamil. Okay. Or maybe Malayalam, or maybe Hindi. So in that case, what will happen? You will be having the English sentence, English paragraph, and then that should be given to the model, and model should translate it into the corresponding language. Now, in that, if you just see that problem carefully, it's like many to many, because we have many inputs, we have many words, because in the paragraph or in the sentence, you'll be having a lot of words, and you have to predict a lot of words as an output, because in that language also, it it will contain a lot of words for making that paragraph of the particular input paragraph. Okay. So whatever paragraph you are giving in one language, it should be converted into another language. So this problem is called many to many problem. Because many input, many sequence, or many words, and many output as a many words or sequence of words. So it has to also capture Like it's not like very simple problem because you are writing something. So it should not individually predict, or it should not predict each word separately, because if it happens, then what will the problem, like your problem would be you will be not getting proper or meaningful sentences, because whenever you are converting one language to another language, then whatever you are getting, whatever paragraph you are getting in that language, there should be the proper meaning of that paragraph. Okay, it should not be uh, meaningless. It's not like so. So that's why I'm saying, like, here only predicting a word is not sufficient. It should predict word in a particular order, so that if you just consider full paragraph, there should be proper meaning. Okay, so we have like two type of mean to many problem. One is like what I already discussed, the first one. So here, what happens? We'll give the paragraph in one language, like this is the word, first word, second word, third word, and so on. And your model will capture the sequential information. It will capture the relationship between all the words. It will capture the information from every word and as well as the relationship, and it will store somewhere. And then once your input is already processed through the model, then it will start to give you the output. Okay, so you can see here. So after every input, here you are not getting output. Once your all the inputs, like all the words of the paragraph, have been processed, then your model has started to give the output. You can see here. So this is like one type of problem. You could be having another type of problem, which is again many to many only. You can see here, it's also many to many, but this is not same as what we have seen here. Okay, in this case, what we are doing, we are predicting output after getting every input. Okay, so like you can just I'll give you one example. Suppose you have to do the frame classification of the video. You have given the video, but I'm interested in getting class of every image of that video or every frame of that video. In this case, we were predicting only one class for the whole video. Now here I want to get class for every frame of the video, every image of the video. So here again, you have the sequential information because you have the video, and in the video, every image is somehow dependent on other images. Okay, so we also have to capture those relationship, but at the same time, it has to give class for every input also. So you can see here, this is the input, processing it and getting the output. Again this, getting the output. Again this, getting the output. But they are also somehow connected, so that they will the sequential information will be captured. Okay. So this is again one another type of problem. So when this RNN, so whatever problems we have seen here, this, in every case, we can use like our suitable architecture, a suitable neural network is RNN. So we should use here if you have these all these type of problems. Even in this case, in the first case, we know that CNN or fully connected, they are very suitable. But people have also tried to use RNN, because whenever any new architecture or new type of network model comes, people also started to use it for all type of problems. Okay, but if it works, is fine. If it's not working, no issue, because we already have the appropriate models for solving that problem. So when RNN came, at that time people also started to use it for the image type of problem. Okay. Now let's see what are the things they have done. So this was the, like, you might be aware of this data set. This is MNIST data set. So we have all those like handwritten digits. Uh, and you like in that data set we have 10 classes, so 0 to 9, and every, like, for every digit we have a lot of handwritten images. So what they have done, they this paper published in ICML 2015, ICLR 2015, and they tried to classify it. Like even previously, also we used to use this CNN or fully connected for doing the classification of this MNIST data set. Now, what people have done here, they have the researchers they have taken this image and they have seen this image as a sequential data. So, image can be seen as a sequence of, like we can say, small grid. Okay, this, so they have seen in this way. So why not we should consider this image as a sequential grid? Okay, and these are called glimpses, and then give this to the model, and then model will see this image as a sequential data, and it will do the classification. So like this. Now here we have, in the case of CNN, we have this will be considered, this is considered as a one input. But in the case of RNN, they divided this thing into multiple part. Okay, and now they have considered this as a sequential data. And now these are the inputs to the model. So we have multiple inputs, and then your model should give one output. Like what is the class of this whole image, or what is the class of these all the glimpses. Like so combining these all the glimpses, combining these all the small grids, what is the class? Okay, so in this way they have solved it. But let me just tell you, this is not very suitable uh, network for solving image classification, because you have a lot of very good architectures for solving it. But again, they have tried it and then they got good results, like promising results. Then they have also used this thing for generative task. And this paper came in ICML 2015, draw a recurrent neural network for image generation. So image generation, whenever you are going to generate the image, the GAN is the suitable uh, type of architecture. And in GAN, GAN is like sort of mechanism, not, I should not say architecture, it's like sort of mechanism that you use for generating the image. In the case of GAN, like whenever you are dealing with images, most of the time we take CNN or fully connected layers for doing it. Okay. Now, what these guys have done, like the authors of this paper, they have considered this they went for solving this problem, and they have used RNN for the generation of the image. And again, if you know that if you're going to use RNN, then you have to go with the sequential type of data. Okay, and you know that image is generally not considered as a sequential data. It's like grid structure, but it's not. There is no. We do generally, because we see full image in a single shot. Okay, we do not see the relationship between like different samples, or maybe there's no concept of that in this case. Okay, now what they have done, they try to make this image data as a sequential data. Okay, like as a sequential generation. Okay, so instead of generating this full image, because when you dealing with the GAN, what GAN does, it takes the noisy just one vector and it will give you the image. That's the goal of the GAN. Even nowadays, some other advanced architectures, advanced mechanisms are also there, like diffusion model and etc. So what it does, it takes the just one vector and then it will give you the image. Now here they do it in a single shot. So just give it, get it. Okay, and most of the time CNN and this fully connected are being used. Now here what they have done, they tried to generate this image in a step by step. Okay, So generate image one piece at a time. So suppose you have to generate this full image where some object is there. Now don't do it in a single shot. Just start with from the one point, maybe this point. Start from this point and then generate every like one part at a time and generate this. So now this can be considered as a sequential generation. So they have also done it and then they got some good results. Okay, but again, let me just tell you that time these all the things came, but CNN was the most popular type of layers which have been used at multiple places. But these all the things were like just for the sake of like just trial and error. Like why not we should use it because if it's giving very good for the other type of like data, then let's try it for the this image data also and let's see like what is happening here and then they have just tried it. Okay, and again, but this is not very suitable for this type of data because we have the better architecture or better layers for this. Okay, so with that, I've just given you a lot of motivation. So even nowadays, whatever we see like Chat GPT, LLM, so we can say this RNN was the starting point for these all type of new architectures. But nowadays we have even more advanced architecture, more advanced layers. But at that time, you can say like this was the benchmark architecture, benchmark network for solving this NLP based problem, natural language based problem. Okay. So with that, let us dive into recurrent neural network. What is this and how it works? Okay, so just seeing the this recurrent neural network, we have X, we have input, and then we have RNN in between, and then we are getting the Y output. Now all the magic is here inside this RNN block. Okay, and let us open this RNN block and let's try to see like what is there. So if you just open this RNN block, we have one recurrence formula. And this recurrence formula, you can see here how it is, what is there. It's taking two things as an input. Okay. One is your HT minus one, another one is your XT. This XT is called the current input, like this, whatever you are giving to the model, this layer or network. And this is your past information, or you can say the past state, old state. So in the state, actually your state is containing the information. It is having the information. So again, we'll elaborate it in a very depth manner. We'll see. We'll also we'll go through the example so that it will be easy for all of you to digest it. Okay. So these are the two arguments. These are the two inputs that is being taken here, and then you apply this function over that. That function is fw. Okay, so function which is parameterized over w. So w is the weights. So w is having all the values that is going to those are going to learn. Okay, so we have weight, we have the function, and that function is parameterized over w weights, and this function is going to apply over these two inputs. So it will take these two inputs and it will do something and then it will give you the new state. Okay. Hmm. Now one good point is this function, the same function you will be using for every state. So whenever I'm saying same function, that means your w would be also same. So whatever state you are going to define for generating every state, this function would be same. Function would be same, and at the same time the weights will be also same. And that's the beauty of this RNN. Only the thing which are going to change are st minus 1 and xt.
So state, the previous state would be changed for generating every other state, and input would be also changed. So current input would be also changed. Okay. So these two things will be taken here, and then it will give you the new state. Okay. Now let's see the formula. What is inside the FW? Sorry. Uh, this is also called vanilla RNN. Okay. Or Ellman RNN also, because it was given by this professor Jeffrey Ellman. So either we say this vanilla RNN or Ellman RNN. So this is the main function, and if I just open this FW, so your FW is this. So what is happening? You are multiplying WHH with HT minus 1 and WXH with XT, and then you are adding bias. Okay, and then whatever you are getting from here, you are applying the 10H, that non-linear function. So if I just see here, this is your fully connected layer. This is also your fully connected layer. First fully connected layer is getting multiplied with the previous state. Okay, and then you are adding this part. And this part is what? This is your, again, you are applying fully connected layer over your input, and whatever you are getting, that you are going to add in this. Okay. So if I just carefully see this part, so this part is what it is doing. It's just enhancing the previous state. Because you know that the goal of the fully connected layer is to enhance the feature or make the robust or make the more suitable features. Okay. So it just or do the refinement of the features. Okay. So whatever information you got from this HT minus 1, and HT minus 1 is the previous state. Now you are taking the help from the previous state, and you are not directly taking that state, the information of that state. Instead, you are first multiplying that state with the fully connected layer. So first you are doing the refinement of the previous state, and then you are doing the refinement of the current input, and then you are adding these two terms. Okay. And then you are also adding the bias. You know, bias will be always there. when So whenever you have fully connected layer, any type of layers, you will be also having the bias. So this part is giving you the enhanced input information. This part is giving you the enhanced state information, previous state information, and then you are adding these two. Now, if I ask you what is inside after doing this, what is the information that we have? So your answer would be, now I'll be having the previous state information along with the current input information, because I have aggregated these two information. Okay. And then you have the bias. And again, you are applying the 10H, because you have to introduce non-linearity, because here this is linear function, this is also linear function. So linear function will not help you always. So you need non-linear type of function, and that's why we generally introduce non-linearity. Okay, and this will give you the HT. Okay, now this is the new state or current state. So you generated the current state with the help of past state and the current input. And now whatever you got here, with the help of this, you can generate output. Okay. So with the help of this, just take the HT. Now your HT is having the state is having the proper information, because the state has this state is being generated from the past state as well as the current input. So this is having the aggregated information. And why it is required? Why you need aggregated information? Because in the case of sequential data, we have to also see the sequential information, the relationship between the sequential samples or sequential. Suppose you are so dealing with the text data, then you have to see the relationship between different words, because one word is not uh, fully helpful. You need to find like the relationship. Then only you will be able to find the meaningful meaning of that particular sentence. Okay. So you also have to capture the information of full sentence, and at the same time you also need to cover every words in a proper manner. Okay, so here you are going through, like, going with accessing every word at a time, but that is your current input. Whatever words you are giving, that is your current input. Like one word at a time, one word will be your current input. But you also need to see like the meaning of the sentence, so that you will be able to, if you're doing the generation task, then you will be able to generate the proper output. Because only seeing one word is not sufficient. It has to also see the information of the sentences, and from where that will come. That will come from aggregating all those previous words, information of all those previous words. So let me just tell you, in some way, we are going to store the information of all the previous word in the previous state. Again, I'll go through the example, and then it will be more clear to you to understand this thing. Okay, so whenever I'm going to predict the output, because this st is not the output, it's like you have generated, it's like your defined features. So you have defined your current input features with the help of the past state features, and now this is your current features, and with the help of this current features or current state, you can generate the output. Okay, so again, for the output, take the st, why is the fully connected layer. So take this as an input, multiply with the fully connected, add the bias, get the output. It's very simple equation. Let us see this thing with the computational graph. Okay, so like suppose you have given the paragraph, or maybe let's take consider one sentence, and you have to process the sentence, and then you have to take the decision. Okay, so suppose in the sentence we have all the words. So we have x1 is the first word, then x2 is the second word, x3 is the third word, x4 is the fourth word, and so on. Okay, and then you have to process these all the words in a sequential order, because they are having the sequential relationship. Okay, you cannot go in any arbitrary order, because if you're going with that, then there is problem. So you started with the first word, and now your goal is to generate the state, and you know that if I'm going to generate the state h1, then I need two inputs. One is x1, and x1 is with me, and I also need h0, past state. But if I start from x1, there is no past information, because we have not processed any word before. Then from where I should get it? So this is like, this is the starting point. So whenever, like, when you are, like, when you have a starting point, at that time we take this, we consider the previous state as 0, and since you know that it, you have not covered any word till now, so you can take this as a 0 0 vector. So again, let me just tell you, here everything is the vector. Your state is also vector, your input is also vector, everything is the vector. Okay, so you can take 0 0 0 0 0 0. That means there is no information in that state, but again, for the sake of applying the formula, you need that. Okay, so that's why this is the initial condition. Or one way is like, you can just set 0 0 0, or you can just give this task to the model. Hey, you just learn it. So your model will itself decide like what are the values I should put here. So these are the ways by which you can do. We can start with the first or initial hidden state. Okay. Now you have to generate the h1. Okay. So what you'll do? You'll apply fw. Now you have h0. You have x1. Generate h1. So again, apply the formula. Fw, that formula, you know that this is like 10h into whh, and then will be multiplied with h0 plus wxh multiply with the x1 plus bias, and this will give you h1. Okay. Now you got the H1. Okay. Now if I ask you like what is there in the H1, you can say, hey, in the H1 we have incorporated, we have aggregated the information of X1 and H0. But in H0 there is no information, so your H1 is containing the information of X1 only at the first at the starting. You have to go further. So suppose I have given one example. This is a cat, okay, and you have to process it. So suppose your X1 is this, and you have done it. You got the H1. Now you have to go to the is. So suppose your is X2. So now you have X2, and you also got this H1 from the previous word, and that previous word was this. Okay, so with the help of this, you have generated H1. So if I say, like, if I ask you, like, what is inside the H1, you can say easily say, hey, in the H1 you have the information of this. Okay, and then you have the information of is here, and with the help of this H1 and X2, you are going to generate H2, applying the same formula, that 10H in bracket and that uh, the fully connected, all those fully connected layers. Okay, now that will give you H2. Now you have processed is. Okay, so you have processed this and is both. Okay, and in the H2, if I ask you like what is the information in the H2, now your answer would be this H2 is containing the information of X2 and H1. And what is H1? H1 is coming from X1. So that means if I just see H2, H2 is containing the information of X1 and X2 both. So it's like refined information or aggregated information of X1 and X2. And this is required because there is relationship here. Basically, I cannot write is this a cat. There is no meaning of this. So I have to go in a sequential order. And that sequential information should be captured. So you are going to capture the information of every word along with this that sequential relationship. So in this way, you can process every word. So now you can go for the third word, X3, then you have FW with the help of H2 and X3, generate H3, and so on. And finally, you will be stopping somewhere, maybe at the last state. Because suppose you have processed all the words of the given paragraph, and now at the end you have to take the decision, hey, what is the suppose you are doing the sentiment analysis, so you have processed all the words of the paragraph, and at the end you have to stop. So that will be the final state, and suppose this is the final state, and at the end you have to take the decision like what is the class of this paragraph. So you now at this point you know where the aggregated information is. So your HT, if I just say you what, hey, what is inside the HT? So you can say in HT we have the aggregated information of all those words which we have covered till now. Because every state is containing the information of all the past words, and that you should realize here. Okay. So in the ST, if I given the paragraph, it is, and if I've shown the full paragraphs word by word, then in the ST is having the information of full paragraph. It's like aggregated information, or we can say the global information of that paragraph. And now with the help of ST, you can get the output. So now give this ST to the one again, one more fully connected layer, HY, and it will give you the class. So the good point is like what I told previously also, that every time we are using same FW and the same function with same W. So this W is like shared across all the states. And that's the beauty, because only one W for these all the things are sufficient for training the RNN. Okay. So number of parameters are not very large because every time you are using the same W. So now you can, like, using this structure, you can solve all those type of problems what we have seen before. So either you can have many to one, or one to many, or many to many, or many to many with a different, like one is like many to many is like we are processing all the inputs and then we are producing every output. One is like for every input you are producing the output. So this is the same problem. Okay, so you just have seen the before. So it's like many to many problem, but for every input we are we are producing the output. So you are giving the like x1 and h0, getting h1, and you know that in the h1 you have the aggregated information of x1 and the previous thing. Okay, so if I say like this is a cat, so first I'm seeing this, and then and past is nothing. So just with the help of this, I'm generating h1, and then I'm deciding I'm just going to get the output of this. So maybe output would be maybe it could be like generating next word, or it could be maybe class. So I'm going to predict the class of this. Just take the hypothetical problem, and then I have to go further. And again, when I process this is when I'm here. So when we are processing is I'm here, and with the help of this and this, I'm generating this h2, and then with the help of h2, I'm predicting the output. So if I'm here at this point, I'm not directly predict the output based on is. Instead, what I'll do, I'll take the help from h2, and inside the h2, I'm having the information of this and is both. So when I am here at this point is, I am going to predict the output based on the information, based on the past inputs like this and is both, because we know that this is somehow related with the it's like they are having the sequential relationship. So we have to capture it. So even so, this is very required thing in the case of NLP or wherever you have sequential information, because every next output is also dependent on the previous every next input is also dependent on the previous inputs. Okay, even on the future input also, but let us just consider the past inputs only. So whatever output, whatever input you are going to cover, this is not, there is no meaning of e. So if e is only meaningful when we have this whole sentence, and that's why we are capturing it. So when we are at the e a at this point, so we are going to decide the output based on the a as well as all the previous inputs, and that is going to store in the state. So your state is storing the past input information along with the current input information. So this is having the aggregated information of those all the things. Okay, so this is one type of problem where you want to predict output for every input. You can see at every state we are predicting the output, and for predicting output again we have why here, which is getting multiplied with this at the state and adding the bias and getting the output. Now during training, your model will give you any arbitrary thing at the starting, because your model is knowing nothing. It's just like starting, it's like child, it's knowing nothing, it has to start. So initially it has given you the output, but those are not reliable output. Those are like most of the time you'll be getting wrong output, and then you know like how to correct it. So you find the loss, you have the actual ground truth, you know like what should be the output here. This is like I'm just talking about the training time. Okay, so find the loss. So L1, L2, L3 and up to LT. So find the loss for every output, and then you just sum it, and just aggregate all the losses, and then you have to do the back propagation. Then you have to change the weights. So that's the again other thing. So we'll come to this part later. How to go back? That is again slightly we can say this trickiest step. So we'll discuss this thing later. But the goal is very similar to the CNN and this fully connected that we have seen before. So here also you have to train it. So you have the W has to be trained, and for that every output you have to find with the help of like whatever outputs you are getting from this model, and just see like you have the ground truth, find the loss, and then loss should be minimized. That's the goal of this. So this is like many to many problem. When you have one to many to one problem, like I have told suppose you have to do the sentiment classification. So in that case, you have to process every word. These are the words. And once you have processed all the words of the given paragraph, suppose in the ST you have the information of all those words, and now you are going to decide like what is the class of this. Okay, so it's just like one time classification. So processing all the inputs and then do the classification. So this is your many to one problem. So here again you will be finding the loss because you are just getting one output. So you're finding the loss at this point. In the previous slide, we were finding the loss at every state because we were getting the output at every state, and then we were aggregating all the outputs, and then we have to do the back propagation. Here you have to find the output only at the end. You have to find the loss only at the end because you are not getting output at every state. Instead, you are getting output only at the end. So you'll be finding L here, and then that L should be back propagated. Or if you have one to many problem, like what I told you, image captioning problem. So you have given only one image, and you have to predict a lot of words in a sequential order. So here again, your input is only one, and with the help of that input, you will be predicting all the outputs. And here again, you also again you have to find the loss at every output for every output, and then in the similar manner that we have seen in the previous slides, you will just aggregate all the losses, and that loss should be back propagated. Now when I say when we were talking this image translation task, so image translation task is looking like a many to many because you have many words and you have to predict many words as output. But in reality, this is combination of many to one and one to many problem because you cannot find output at every state, because if you are going with that, you might be in trouble. Why? Because if you are predicting, suppose you are if suppose I'm writing something, this is a cat, and for every word you know that we have a state, you are generating one state, and with the help of a state, if you are predicting some output, predicting the output, then what will happen? Like suppose you started with this, and for the this you are predicting. Suppose you are doing the translation in Hindi, so for this you are writing yeah, and then when you are reaching to is, now again if you are predicting the output at this state, now you'll be predicting high, and then again if you reach here, you're predicting ek, and you'll be predicting belly. There is no meaning of this. यह है एक बिल्ली. It is not proper sentence of the Hindi. So when you go with this way, this is not helpful. So that's why when you are solving image translation problem, this is not like directly many to many. Many to many means like for every output you are just predicting the for every input you are predicting the output. Instead, we are following many to one and then one to. This is also one type of many to many problem, but it will not go in a direct manner. So first you aggregate all the information of all the words. Okay. And once you reach to the final state, like once you process all the words here, then you start to predict the output. So like you can see here. So these are the words that you are just processing. So suppose this is a cat, so you're processing all the words. And then you're processing all the words, and finally you're reaching here at this point. Now in the HT, if I say like what is inside HT, so you can say, hey, in the HT we are having all those the information of all those words which have been covered till now. Okay. Now we have to translate. Now need to do the translation. So since HT is having the information of every word, so now I can go for translating it into another language. Okay. So now, because it should give the proper meaning of the sentence also. It should not be a like meaningless sentence. Okay. So just getting the meaning of the word is not sufficient. We should be having the proper sentence. Okay. Grammatically correct sentence. Okay. So now at this point, once you reach here, now from here you will start generating the output. So you can see here. So you'll be having this is like one set where you have shown all the inputs with the help of W1. This that is your like the function. This W1 is shared across all those states here till this point, and then we have this another uh, set where this st will come here, like this st will come here, and then with the help of this ht it will generate, like it will start to generate every output. So you can see here this h2 this is coming here, and then it started to generate y1 y2 y3, and it is shown. So it's like uh, first we are encoding, this is the encoder part, like encoding the information. So we are encoding a lot of information in a single vector. Okay, so encoding all the information of every word in this ht, and then we start to decode it. So now from ht, now just decode all those words of the corresponding language. Okay, so with that, let us take one example, and then that will give you more clarity, like how the things are happening. So suppose, let us take one example. Suppose we are taking one word, hello. Okay. So hello word is like, in general, we work on word level, but let us work here on the character level, just for the sake of just this is sort of 2i example that we are going to see here. So suppose we have given the word that is hello, and we are like we have to work on the character level. Okay, in general we'll not work on the character level, but here just for the sake of just for sake of 2 example. So in this hello we have different, like just find the distinct character. So we have distinct character like this, h e l o. So these are like vocabulary. Okay, okay, so now we have to, like this, we have to solve the problem, and let us consider this problem as a next correct character prediction problem. Okay, so just looking the current character, you have to predict the next character. So first what we'll do, like whenever you are going to solve some NLP problem, the thing is that you cannot give these all the text or these all the characters as it is. Okay, okay, because you know that your model will accept the numerical values. So the first thing is like you should convert it into the numerical values, and uh, since here we have four different words, four different characters. So what I will do, I'll assign one vector to one character. Okay, so we have four words, so four characters. So I'll just give one hot encoding for every character. So this is also one type of representation, numerical representation that we generally use it when we are going to convert like any character or words into the numerical values. So let's understand this very simple thing. So here, like we just see like how many vocabulary we have, like how many characters we have in total. So let us assume that uh, in this problem statement we have only four different characters. So that means I'll make the four-dimensional vector. Okay, so I'll make the four-dimensional vector, and one would be hot and remaining will be cold. Okay, so one hot means like it will be having the one. Okay, so for h, I'll give the vector four-dimensional vector, and first dimension will be having one and remaining will be having zero. Similarly for e, I'll give the second dimension as a one and remaining will be having zero. Similarly for l, I'll be having 0, 0, 1, and 0. And fourth, 0, 0, 0, and 1. Okay. So these are like four different vectors, and one vector is assigned to the one character. Okay. So now you have converted your character into numerical values or in the vector form. Okay. And now instead of using this character, I'll be using this vector because this vector is the representation of the character. Okay. So I'll start with like now let's write the all the inputs. So since I have this hello, so and every time I have to predict the next character. So I'll be having first time I'll be having H, then I'll be having E, then I'll be having L, and then I'll be having L. And after that, I cannot go with O because O after O there is no character. And goal is to predict the next character. So L, this last L will predict the O. Okay. And our job is done. Okay. And these are the characters, but I'll take the vector of every character. So this is the vector of the first character 1 0 0 0, then 0 1 0 0, then 0 0 1 0, and 0 0 1 0. Both we have same because these are the same character LL. Okay. Now the next goal is what? The goal is to generate the state. Okay. So with the help of this H, you are going to generate the state H1. With the help of this first character, you are going to generate the state H1. Now you can decide like how many values or what would be the dimension of the state. So in this case, we are just assuming that input dimension is 4 because it's coming from the one hot encoding. But hidden like this state dimension we have fixed as a 3. Okay, but this is your choice. Okay, this is again hyperparameter, so you can set it. So we have set it as a 3. Okay, so whatever you are doing here, your state will be having the dimension 3 only. Okay, and that should be taken care in this doing this formulation. So at the end, whatever you are giving here, yeah, it should give at the end three-dimensional vector because your state is having the three-dimensional. It's like the size is of three dimension only, three only. Okay. So now what we'll do? Now the things are very very simple. Here you can say like just apply this formula. So when we are here, you take this is your x1. This is your x1. So you have just wxh, and then that will be multiplied with the x1. This is your x1, and then we have whh, whh, and then we have h0. Okay, and then you will apply 10h over this, and you will get the h1. And this is the h1. And this x1 is having dimension what? It's like 4-dimensional vector, so it's like 4 into 1. Then h0 is having what dimension? You since you have considered state as a 3-dimensional vector, so 3 into 1. Now, what is the dimension of this fully connected? The answer is very simple because you have to generate the state at the end, and the state is having the dimension 3. So this XH, WXH, this fully connected should be having the dimension 3 into 4. So that this will be multiplied with 4 into 1-dimensional vector, and it should give 3-dimensional vector. And then we have to, as 0 is 3 into 1. So here again, for WHH, what will be the dimension? 3 into 3 only, because it will multiply with the 3 into 1-dimensional vector, and it will give you 3 into 3 into 1-dimensional vector. And you will be also adding bias here. I just forgot it. So BH, and bias will be also of having dimension 3 into 1. And these all the things will be added. Apply 10h, and that will give you h1. So this is the h1 that you are getting. In the similar manner, you can get h2, h3, h4. Now the thing is, for every state, like for every input, you have to generate the next output, next character. So whenever we have h as input, now I have to generate e as output because the next character of e is h is e. Okay, so you got the state. These are the states that you can get at every for considering every input. But for every state, you also need to generate the output because it's like next character prediction problem. So for every input, it should predict the next character. So with the help of this, it should predict next character. So this again, you will be having WHY here, which will be multiplied with the state. and then it should give the next character. So again, this problem can be seen as a classification problem because every vector is having one hot encoding, and every character is having one hot encoding vector, and every character can be seen as a one, like this can be seen as a character classification problem. So you have to predict the you have to classify among these all the characters. Okay, so from H it has to, but it has to give the next class, the class of the next character. So wherever you are giving H, then it should give the class of the class of the next character. Like what is the class? It should give E. So E is the class, next class. Okay. So whenever I'm giving H, then you're getting it, and then again it should give the four-dimensional vector. Why? Because we have one hot encoding representation, and you know that in what one hot encoding representation, whichever is, like, again you apply the softmax probability, so whichever is giving the maximum value, maximum probability, you'll consider that as a class. Okay. And that is very easy in this case. Why? Because you have, like, these are the classes. So H, whenever H, then first index should give the maximum value, or it should be close to 1. If it is E, then second index should give the maximum value, or it should be close to 1. If we have L, then third. If we have O, then we have fourth. Okay. So in that way, like which index should give the maximum value. Okay. So now in this case, suppose you got these all the four values at the end. Okay. Now how you are getting it? So you got this H1, and now you multiply with WHY, which will give you the output Y1. So H1 is having 3 into 1 dimensional vector, then you'll take this as a 4 into 3 dimensional vector. So that will be getting 4 into 1. So you are getting 4 into. Now just have to see, like, what is the value that you are getting at this position. Because this is the index of the actual class. Because giving the H, you have to predict E. And E is having 1 at this point. So this index should be having the maximum value. But in reality, at the starting, you will be not getting it because your model is not knowing, like, what should I predict here. So then you will be finding the loss. So you will apply the cross entropy here between this E, the actual vector of this, that is 0, 1, 0, 0, and this vector, and then you minimize it. Similarly for this also, this also, this also. Okay. So whatever I told, the same thing I'm going to recap here. So again, with the help of H, you're finding the state and then you are predicting this. Now this should be E because your target character is E. Because given the H, I want to predict the next character, that is E. Now whatever it is giving, it might be wrong because it's giving the maximum value at this point. But that means it's saying that this is O. But it's not O. It should be E. So your target character is here, and you got this, and now you have to find the loss. So just apply the cross entropy because we are considering this as a classification problem. So once you do it, now go for the next. So suppose it has given let us assume that it has given something, or maybe you got it, like you got this thing, and then you just find the loss, and then go for the next, predicting the next character. Now next character, like we have to predict with the help of E. Okay. But when you are, since this is sequential relationship, because E is not meaningful, because it's meaningful when we are combining these all the words, all these characters, and that's making the hello. Okay. So hello is having some meaning, but E is not having meaning. So that's why, like, when you are at this point E, then you also see the information from the H. So aggregated information, and where that aggregated information is, that is in the state. So this state, if I just see H2 here, H2 has been constructed from this and this. So indirectly, it is containing the information of this as well as this. And now we are again going to apply here HY, getting this output. Now here, whatever you are getting, like maximum value, is just see like where we are getting the maximum value. This is giving the maximum value at this point, but it should give maximum at this point because the next character of the E is L, and for the EL, this is the representation that I want to get, but it's not giving that. It's not giving maximum value at this point. Then that there is loss. Find the cross entropy loss, and again it will be like later it will be like back propagated. You have to minimize it. Similarly, like once you reach here, now you have covered H, E, and now you have reached at L. Now again you have this representation input, and you have the previous state. This is the past state. With the help of this and this, you make this, and then with the help of this, you you generate this. And you know that what is the target character here. So you have given the L. It should give L again because after this first L, you have L only. Now whatever you are getting, this might be wrong, and it's giving the. But in this case, it's giving. Here you are giving the right result because this point is giving the maximum value. But in most of the cases at the starting, it will give you wrong values. Okay, and then you have to find the loss. Even if you are getting correct value, then also you have to find the loss and cross entropy, and then that should be like all those loss should be aggregated and it should be minimized. Okay, so because every time you know the target, so you can get the loss. Then we are done till this point. Now you are at this point. So now you have covered now final this L. Take this L, generate this state with the help of this and this, and then generate the output. Now this output should be having the maximum value at this point because O is having 1 at the end. So it's giving that. So we will be happy in this case. Still we'll find because we have to somehow maximize it. So it's getting 2.2, but still we can go further. So that's why we generally take the cross entropy, this apply softmax at the end, so that values would be converted into probability values, and then we'll maximize the value of the actual class, the probability of the actual class. Now this is done. Okay. Now the thing is, this is when we are doing the training. So while training, you know all the inputs. You know this hello world. So that's why you can arrange these all like you can arrange these all the inputs in this order because you know these all the inputs in advance, and you also know the target, like what should be the next character, and based on that you are just training it. Okay. Now the thing is, while testing, at the test time, you don't know the word. Suppose you have trained the model, and then I'm saying, hey, you take the H and generate me the word. Now, since your model has been trained to predict the next character every time, so if it is taking the, like if I'm giving the initial character, your model should give the word. So during testing, we are not going to give the full word. Instead, I'll just give you one character of the word, and you have to predict the word. Your model has to predict the word. Okay. So if you're doing it, so suppose you have given the H, and then it got the hidden layer, like it generated the state, then output the WHY, then it has been converted into softmax, like it has applied the softmax, and then it got the maximum value at this point. And if I'm getting maximum 0.84 probability at this point, then I'll just convert into, I'll say, hey, this belongs to this class. And what is this class? This class is like what is this class? This class is E, because E is having 0, 1, 0, 0. That means it is having the maximum value at this point. So I'll say, hey, this the class of this is E. Now, how to proceed? So with the help of H, I have predicted the E because H was given to me. But after after H, we do not have any characters that those are given to us. Then how to proceed? So idea is very, very simple, because you know that every time your input is predicting the next character. So next character would be the input for the next state. So you got E here. Now E would be given to the, E will be taken as a next input. Okay. So take E from here, and you take the one hot representation of the E, that is 0, 1, 0. And now with the help of E, you should predict the next character again. So going here again, you state, generate the state output again. Suppose it has given you L, because this is having the maximum value, maximum probability. So you'll say like it's like L. Now L will be given as an input to the next. It is considered as an input for the next, uh, like for the next step. So is take this L here, then take the one hot representation. This is not one hot representation, because this is just like probability value that you are getting, but it's not giving you one here. Instead, you are getting the maximum value, and we assume that this is the, this, since I'm getting maximum value here, so that means it's close to 0, 0, 1, 0. Okay, and that's why we give class to this L. But when you are going to give input, then it should be given in a one hot representation. So now you convert it. So once you got like the, this is giving L, now you can just get the one hot representation of the L, that is 0, 0, 1, 0, and then give to the next state. Uh, give to the, give for generating the next state, and again it will generate the next character, and in this way you will proceed, and you will stop somewhere. So maybe at the word, now you are fine that you got the word, and you stop here. Again, let me just tell you, this is just toy example, but in reality, because again, this is also one problem, when to stop. So in reality, you should be having starting token and token. Like you should be having a starting character. When you are dealing with character, then you will be having the starting character and the end character. But in most of the cases, we don't deal with character. Instead, we deal with word. Okay, but this is the toy example. That's why I've given this here, just as for the sake of understanding. Okay, so I think I'll stop here, and you guys can ask question here at this point. Go ahead.
Yeah, hello, sir. Sir, can you
Hmm.
go to the initial slides of the language modeling? Initial slide, the first or the second one.
This.
Yeah, yes. Here the values of the this input, not the input layer, the hidden layer, like zero point 0.3, minus 0.1, 0.9. So all these
Yeah,
values
here
are
states.
hyperparameters.
Uh, these values are coming from like applying this function. Na? So like you're generating next state every time. So you are generating the next state with the help of the previous state, or you can say like where you are generating the current state with the help of the past state and the current input. And this and this, these two are like fully connected layers. So WHS is getting multiplied with this HT minus one, and this is multiplied with the XT, your current input like X1 here, and then you are also adding bias here, and then you are applying 10H, and then you are getting this HT, and this HT means like in this case it is H1, and this is your H1. So in H1, these all the values are coming from multiplying these all the things and summing it. So
Yes, sir, getting.
this is not hyperparameter. This the size is the size is your hyperparameter, because you have decided this size as a 3. But values are not the hyperparameters. Values are coming from like multiplying your input with the fully connected layer, multiplying your input as well as your this past state with the fully connected layers, and then summing it. Okay. So this function is giving you this these all the values.
Okay. Yeah. Thank you, sir.
Thank you. Thank you. But this is very, very useful, like when you are going to develop any sequential type of, you are going to solve any sequential type of problem like NLP. For NLP, this is very, very useful, because this is the starting, this was the starting point. Nowadays we have transformer also. So again, I'll cover that transformer. Uh, but again, yes, for transformer also you need to understand this thing, because otherwise you will not appreciate the transformer.
Yeah.
Because our speed is fine, like, because I think we'll be able to cover till transformer. Then at the end I'll give you some, maybe some brief introduction of all other concept. That's sufficient, because many of you might be using transformer type of architecture maybe in your work, or maybe your project, what you are going to do next year. So that's why that is required. So that's why I thought of putting that here. Otherwise, you know the concept. You are aware of all those concepts, and all those new architectures, new networks, whatever are coming, those are not totally separate or isolated thing. They are coming from these all the basic concepts only. So if you know the basic, now you can easily understand, you can easily grasp the things from the new, or all those new architectures or new networks. So that was the goal of this course. And somehow, like, all the basics have been, almost all the basics have been covered, except this RNN and transformer. Like in RNN, we'll be also covering LSTM, and then we have transformer. And then I'll just touch this generative part, like generative model. Just I'll touching it. I'm not going into depth, because that is again separate course. Okay.
Okay, sir.
Any other question? Otherwise, I'll stop here.
No, nothing, sir. Thank you.
Hello, sir.
Yeah.
So yeah,
Yeah,
please,
I have
some
one
say.
last query.
Uh,
Yeah. So we have double of HY, right? So
uh,
is this same for all the layers or only for output layer, final output layer, sir?
WHY you are saying. So whenever
Yes.
you are using, wherever you are predicting the output, you'll be using same WHY.
Okay.
So if you are predicting
So
only at the end, then you will be having only, like, you'll be using only one WHY. But suppose you are predicting at every state, so you'll be using the same WHY at every time.
so here we have HELL. So here we have 4 HY, 4 double HY, right?
Or H,
Like
what is saying?
so I'm saying that we have here input characters are HELL, right? So
Yes.
here we are predicting each letter, right?
Yes, we are predicting every next letter, every next
Yeah.
character.
So here this means we have 4 double HY, right? Right?
Four.
Okay.
Four vector. You're talking about four vector or
4
four H
vectors
state.
as well as.
Yes. We need four state,
Okay.
because every
Okay.
state will predict one next character. So you have to go with the four state. Then only you will be covered full, like all the characters of the given word. So
Okay.
H, taking the H, it will predict E. Taking the E, it will predict L. Taking the first L, it will predict the second L. Taking the second L, it will predict the O. So that's why we have four. And
Okay.
every character is giving you, like, you're getting the state from there. And then at every state, you are predicting the output. So you have WHY at every place here, sitting here.
Okay, sir.
But
Got
these are
it.
like same copy.
Okay.
That's the beauty, because parameter wise is less only.
Okay, sir. Understand. Thank you, sir.
Okay, so then I'll stop here. If you guys are feeling difficulty, you should ask. You may ask, like, whatever questions you have, please ask. Okay.
Yeah. Yes. Thank you, sir.
Okay.